Hello everyone, let's continue with radioactivity. So we have three radioactivities. The first one is alpha decay, next is beta decay, and the third one is gamma decay. I'm not here to read to you the reaction equation. I'm just straight away going to show you the difference between alpha, beta, and gamma reaction. So the first one is alpha decay. You will see the distinct for alpha decay is when it produces alpha particle. Now alpha particle is actually the helium nucleus, so it is positive 2 plus, but this is a very short lived and it's highly, because it is 2 plus, it is highly charged, so immediately it will try to grab on any electron from any matter that it touches, normally within few centimeters, and then it becomes neutral, which is it becomes an atom. So that's why you didn't get to see that 2 plus. And obviously the one that we want from radioactivity is the energy. Next, we look at beta decay. Now, beta decay consists of two types. The first one is beta plus decay or the beta minus decay. You will see the difference in terms of the neutrino. Here, for the beta plus decay, you will see neutrino. For the beta minus decay, you will see anti-neutrino. And again, we want to get the energy. And lastly, it is gamma decay. You will see that the difference amongst these three decays, you will see for the gamma decay, it is about the excited parents and the stable parents. They don't normally change from one element to another. It is mostly from just being, the parent is being excited, and then it will release its energy, and then it's still the same parent, but more stable and less energy. Now let's go deeper to radioactive decay. It doesn't matter if it's alpha, beta, or gamma decay. We just want to go to the radioactive decay itself. So we have 1, 2, 3, 4, and 5 equations. Let's go deeper. So the first one is a decay rate. Now decay rate is dn with dt equals to negative lambda n. N is the number of nuclei. Nuclei is the plural for nucleus. So negative sign means that the number of nuclei starts to decrease. And then lambda is the decay constant. dn dt is the rate of depletion, number of nuclei. So the unit for the decay rate is decay per second. Next, we have decay activity. Now, activity is represented by the letter A. A equals to lambda n. Again, lambda is a decay constant, and n is a nuclei. The unit for decay activity is Curie or becquerel. Next, we have half-life. T, half equals to ln 2 over lambda. Again, lambda is a decay constant. Unit for half-life can be second, minutes, week or year or decades. Now, I have talked about decay constant again and again in the previous equation. Now, what is decay constant? Decay constant equals to dt over n with the negative sign. The unit for decay constant is per second or per minute or per week or per year or per decade. It depends on what unit of time is given in the question. Now, this one is the equation for number of moles. Number of moles equals to mass of the specimen divided by molar mass. Now, remember that molar mass in chemistry is given in grams. So, you need to change it to kilogram first before you can do the calculation. Okay? And then we have N, which is again the number of nuclei. Unit is atom, because sometimes, 1 atom, 2 atoms, 3 atoms, and so on. So, it's integer. And Na is the Avogadro's constant, which is 6.02 times 10 to the power of 23 per mole. Sometimes in the question, they will ask you about the decay with time. Decaying process in a radioactive decay happens one time, but you can see in 3 different perspectives. The first one, if you want to look at the number of nuclei with time, then you're going to use n equals to n naught exponent negative lambda t, where n naught is the initial number of the nuclei, which is the time t equals to 0. And then you can also look at the remaining activity after that particular time that you want to see in the question. So you can say that A equals to A naught exponent negative lambda t. And if you want to see the remaining mass after that time t, you can get M equals to M naught exponent negative lambda t. Now make sure that the unit of time for the decay constant is the same within the unit of time that you want to multiply. So you have to be very careful. So again, the decay happens at the same time. It's just a matter of what quantity that you want to see, whether you want to see the number of nuclei, the remaining activity, or the remaining mass after that particular time. In the decay activity equation, I've mentioned about Curie or becquerel. So let's see what's the difference between Curie and becquerel. This is the unit conversion for activity that I've mentioned just now. 1 Curie equals to 3.7 times 10 to the power of 10 decay per second, or equals to 3.7 times 10 to the power of 10 becquerel. So 1 becquerel equals to 1 decay per second. So other unit you can use for activity is nuclei per second, or decay per minute, or decay per day, or decay per week, and so on and so forth. So it depends on the question. Lastly, what is physics without graph? So here is the graph of number of nuclei versus half-life. So on your y-axis is the number of nuclei. The unit can be either atom or nuclei. Here, number of nuclei is n and not z, which is the nuclear number, because nuclei is a plural for nucleus, not the nuclear number, because nuclear number is all the number of protons and neutrons in one nucleus. And we are not talking about all the subatomic particles, which is neutron dengan proton ya, dekat dalam satu nucleus. No, we are talking a lot of nucleus, and that's why we call it nuclei. So be careful with that. It is not Z, but it is number of nuclei, which this time we call it as N. This is not neutron. This is nuclei. So here on the x-axis, we have time. So N is the, and this is, I'm going to call this one is N naught, better. Okay, so from the N naught, we get half of it. If it becomes half, this is our first half-life. It is half from the half, it is our second half-life, and so on and so forth.
Alright, let's continue with the tutorial. A radioactive nucleus of radium undergoes a radioactive decay and forms radon. So this is radium-226, undergoes a radioactive decay and forms a radon with a known nuclear number and a known proton number. And we have 42 helium and also energy. The first one is calculate the nuclear number of the radium. So nuclear number is given by A. In order for us to get the A, we look at this one. This is 4. We minus 2 to 6 with 4 in order for us to get the A. For that, we get 2 to 2. Question B, calculate the proton number. So the proton number is Z minus 88 with 2. And the answer is 86. Question number 3, determine the type of radioactive decay. And because here we have helium nucleus or helium atom, this is alpha decay. We know that this is an alpha decay. Question 2, a radioactive nucleus undergoes beta minus decay, was shown below. So we have X with the nuclear number and the proton number unknown. And we have the daughter of 131 and 54 proton number. And then we have beta minus decay. We have also antineutrino and also the energy. We have to calculate the proton number of X. X is the parent. So based on this, we have the 54 and negative 4. And from that, kita tolak dengan 1. So kita dapat 53. Question B, calculate the nuclear number of X. So nuclear number is this one, A. The actual neutron number is the same. This is because none of the nucleon is taken out to become beta. With that, the answer is still 131. Question C, the number of neutrons in Y. So here we have all, which is a neutron plus proton. Well, this one is actually just the protons. And for that, in order for us to get the neutron number, 131 minus 54. And we got 71 neutrons. Let's continue with question number 3. A 1 times 10 to the power of negative 6 kilograms sample of cobalt-60 has an activity of 1.13 curie. The molar mass of the cobalt-60 is 60 grams per mole, and then we have to calculate the number of moles of the cobalt-60 in the sample. So number of mole can be represented by the letter small n. We're going to use n equals to m, which is the mass of the sample, divided by molar mass. And again, you have to remember that you have to change the molar mass from grams to kilograms, because the kilograms is the SI unit for mass. We're going to use 1 times 10 to the power of negative 6 divided by 60 times 10 to the power of negative 3. 60 as in the grams changed to kilograms. The answer is 1.67 times 10 to the power of negative 5 moles. B, the initial number of the nuclei in the sample. Number of nuclei can be represented by the letter capital N. We're going to use this equation, rearrange it, and equals to number of moles times Avogadro's constant, 1.67 times 10 to the power of negative 5 times 6.02 times 10 to the power of 23, and the answer is 1 times 10 to the power of 19 nuclei. Question C, the activity of the sample in becquerel. So the value are given in curie, we need to change it into becquerel. We know that 1 curie is equivalent to 3.7 times 10 to the power of 10 becquerel. So we just multiply the activity in curie with the becquerel. The answer is 4.18 times 10 to the power of 10 becquerel. Question D, the decay constant. Decay constant is lambda. Now that we have the activity and also the nuclei, might as well just use decay activities equation for us to get the decay constant. Rearrange the equation, lambda equals to A over N. Substitute the values, so it's 4.18 times 10 to the power of negative 9 per second. Next question, the half-life of the cobalt-60 in years. The half-life equals to ln 2 over lambda. We substitute lambda, so it's 1.66 times 10 to the power of 8 second, because we have to get it in year. So 1 year is equivalent to 3.15 times 10 to the power of 7 second. So the answer is 5.21 years. The last question, question F, the mass of the sample after 12 years. We need to get the time in second first. We know that 1 year is equivalent to 3.15 times 10 to the power of 7 second. So the answer is 3.78 times 10 to the power of 8 second. And then from here, we're going to use this equation, m equals to m naught exponent negative lambda t. This is the initial mass, this is the decay constant, and this is the time for 12 years in second. The answer is 2.06 times 10 to the power of negative 7 kilograms.